Welcome and good day. Our topic for today, we'll be discussing on how to calculate protection release setting for double-ended LB switchgear in camera relays. Okay, this will be our main single line diagram. This is only a 400 LB switchgear single line diagram. Our subject right now are these relays, this which is installed on the incomer of the LB switchgear. Okay, and this is our relay. This is a multifunction relay, and this is composed of a protection relay and at the same time a metering device as well. So our topic for discussion will be using this F60 relay under GE. Okay, this is a feeder management relay. Okay, right now we have two voltage transformer. One is connected on the secondary side of the transformer or on the incomer. Okay, and the other one VT is connected on the bus of the LB switchgear. Okay, so we have here also a current transformer which is connected on the incomer side of our LV switchgear. Here we have an air circuit breaker. Okay, but for this topic, okay, since we are having a relay, okay, we are going to disable the LSIG tripping circuit of our air circuit breaker. Okay, next. Okay, as I mentioned earlier, our subject relay is GE Multi-Link F60 feeder management relay. This having the following functions. We have here relay 51, 51 and 50G, 27, and relay 25. We will not be using here for this discussion relay 50, and this will be disabled as well. Okay, here, so these relays are in the following incomers. Okay, for bus A and bus B. Okay, and this is our transformer is rated to MVA, and we have here also our three-phase fault, which is rated 335.43 kiloamperes. We're going to utilize this one when we're going to calculate our TDM or time dial multiplier. Okay, so these are the 5 relays that we're going to use for our discussion. The first one is relay 51 or the phase time delay over current relay. Relay 51A, the neutral time delay over current. 50G, the ground instantaneous over current relay. 25, the synchronism check relay. Okay, so we have this synchro check relay because, you know, in our single line diagram, we have both bus A and bus B, and we have the bus coupler. There is a tendency or instances or situations that both bus A and bus B will be synchronized, or both source 1 and source 2 will be connected in parallel. Okay, and we have also 27, relay 27 for the phase under voltage. So these are the ratings of our CT and PT. Our CT is rated 3000 ampere. Okay, the ratio is 3000 is to 1 ampere plus 5P20, while our PT or our voltage transformer is the ratio is 400 is to 110 with class 1.0. Okay, so we have here 3000 ampere because it is based on our transformer secondary current, which is close to 3000 ampere. We have here 2886.84 ampere. Okay, so we have here also our zero sequence current transformer, or also being called CBCT, or core Bosching current transformer rather, and it is, the ratio is 400 is to 1 ampere. Okay, so the location of our zero sequence current transformer, it is connected to the grounded neutral of our station transformer, because on this CT, this will be connected also to our ANSI relay 50G for the instantaneous overcurrent relay, a ground fault overcurrent relay. Okay? Okay, so now let's start on our relay setting calculation. First, let's discuss on the phase time delay overcurrent relay, or the 51 relay. Okay, so we're going to check now how we get this phase time overcurrent pickup of 1.44. To arrive this, we need only to multiply the transformer full load current by 150%. So our transformer full load current on the secondary side is 2886.75 ampere. Then this is being multiplied by 150%. Okay, this 1.5. And we have now the pickup current of 4330.13 ampere. Okay, so the TOC pickup, okay, this will be multiplied also by 1 over the CT ratio, or we have here being multiplied by 1 over 3000. Okay, so that's why we have this value. The set phase pickup TOC is 1.44 per unit. Okay, so our phase time over current curve, we will be adopting the IEEE very inverse. Okay, so next, this will be our coordination time interval, CTI. We'll be using this one later, okay, to compute the our TDM. Okay, so here, this is our subject breaker, wherein our relay is connected, okay, for both for the incomer of LB switchgear. Okay, this is for the bus A and for the bus B. Okay, we have here for our bus coupler, the time delay assigned to this discussion is 0.1 second. Here, this breaker, the subject of our discussion, okay, we have assigned here the time delay of 0.4 second. Okay, upstream, okay, we have here 0.70 second. This is for the primary side of the transformer. Okay, and on the incomer side of the 11 kV switchgear, we have also here the time delay of 1.0 seconds. So here, the time interval, if you notice from here, we have here 0.1, 0.4, 0.7, and 1 second. The time interval here is 0.3 seconds. Okay, so in our point of discussion, our time delay is 0.4 seconds. So from seeing this, we have performed a proper coordination in terms of our time delay. Okay, so we have here in order to solve the pick up in terms of fault current at 200 volt current pick up at 400 volts side. Okay, here this is the fault occurred. This is we're going to perform a short circuit analysis, okay? Minimum short circuit analysis. We have this value here. So we have here a 35,430 amperes. So this will be used to determine the pick up current for the fault, rather for the fault current. Okay, so this will be multiplied by the ratio of the CT. So we have here 1/3000. Okay, so we have here the result is 11.81 per unit. Okay, so we have here the formula to calculate our multiplier setting or the time dial multiplier for ANSI terminology. Okay? Here, this is a standard formula even you are using IEEE curve or the IEC curve. Okay? So we have here, this is for the operating time is equal to the multiplier setting. Okay, these are the constant value, A, B, and P. These are the constant value. And I stands for input current, and this one is a pick up current. Okay, so we have here from the IEEE standard, this A, B, P constant, these are given already from the IEEE standard. So for A, we have here 19.61. For B, we have here 0.491. And for P, we have here is equal to 2. Okay? So, our operating time will be 0.4 second as we discussed earlier for coordination with upstream relays as well. Okay? So, this I pick up here, this is the ratio. Okay? So we have here the 8.18. Okay? So to solve for the multiplier setting, we're going to substitute here for the time, we have here the 0.4 seconds, right? Okay? And for this ratio, we have here 8.18. Okay, that's why here, and the P, we have here 2. So that's why we have here 8.18 square. Okay, and A, let's substitute the value. A here is 19.61 and B here is 4.91. Therefore, okay, our setting for that TDM or the multiplier setting is 0.51 based on this given values and based on our actual short circuit on the secondary side of the transformer. Okay? So, this is the formula that we have discussed earlier. Okay? The same formula also when we're going to use the IEC standard. Ours, we use the IEEE standard, very inverse curve. So we have here the value constant for A and for B and also for C. For IEC standard, the value for C is equal to 0 only. Okay. Please take note that TMS and TDM are analogous terminology. Okay. For IEC, it is called TMS, time multiplier setting. For IEEE, it's called TDM for the time dial multiplier. Okay? Okay. Next, we're going to calculate the neutral time delay overcurrent relay setting or the 51N. Okay. So, for that, the pickup will be 30% of the transformer LV full load current. Okay. So, 30% for the transformer full load current, our full load current is 2,887 when it is rounded off. Okay. So, the pickup current will be 866 amperes. Okay. So, this will be multiplied to the ratio of our CT. That's why our neutral TOC pickup is 0.29 per unit. Okay. So, our neutral TOC curve will be definite time. Okay. And our neutral TOC TD multiplier will be 1.0. Okay. Next, we will be calculating on the ground instantaneous overcurrent relay setting or 50G. Here, this relay, this is connected to the zero sequence uh, current transformer, which is connected also to the grounded neutral of our station transformer. For that, we're going only to limit the current, the ground fault current to be less than 20 amperes. That's why here, we assign here the pick up to be, I pick up current to be 20 amperes. So, multiply the ratio of our zero sequence current transformer, which is 1 over 400. Okay? So, our settings will be, the ground IOC pickup will be 0.05 per unit. Since this is instantaneous, our ground instantaneous overcurrent delay will be 0.03 seconds. Okay? Next, we will be discussing on the phase under voltage relay. Okay. Normally, we need to have at least 80% voltage on our buses. Okay. Beyond that, the relay will operate and trip the system. Okay, or trip the breaker. From here, we'll be using 80% of 400 volt switchgear bus voltage. Okay, so this will be 0.8. This will be multiplied only on the bus voltage times also with the 1 over the PT ratio. Okay, so we have here the value of 88 volt over the 110 volt. Okay, this is for the secondary. Okay, that's why our phase under voltage pickup is 0.8 per unit also. Okay, so for our phase under voltage pickup delay, it should be, yes, it should be a little bit longer. Okay, it's okay because we have here 3 seconds. Okay, beyond that, it's not for we could say it's not acceptable anymore because a prolonged under voltage on our interconnected devices will create overheating on our interconnected components. Okay? Next. Here, we have here the synchro check relay or the ANSI 25 relay. As discussed earlier, there are instances that both buses, the bus A and bus B, or the source 1 and source 2 will be connected in parallel. Okay? For 2 power sources to be synchronized, okay, these are the following conditions must be matched. First, voltage. Second, the phase rotation. Third, the phase shift. And fourth, the frequency. Okay? For the voltage, okay, 2 power sources that are to be parallel ideally need to have the same voltage. If the 2 power sources with unequal voltages, unequal, and speaking on unequal, are parallel, it causes reactive power VAR to flow between the sources. Minor variations is 1 to 5%. This is allowable. That's why we have here 5%. We set the 5% of rated voltage. Okay? Can cause can usually be tolerated. Okay, this is acceptable, 1 to 5%. VAR flow will cause unnecessary heating in interconnecting components if it is beyond that 5%. Okay, it is preferred that the voltage of 2 sources be as close to nominal as possible to avoid reactive power or the VAR flow. Okay, so here we use the maximum allowable value, which is 5%. So 5% of 100 volts, that's why we have here the 20 volt setting for the maximum voltage difference. Okay, next, for the phase rotation, okay, two sources that are to be parallel need to have same phase rotation. That is either both ABC or both ACB phase rotation. Okay? Opposite phase rotation can cause significant short circuit current during paralleling. Okay, so this will be finalized, during the pre-commissioning or commissioning of the switchgear. It has to be ensured that source 1 and source 2 has the same phase rotation. Okay? And the third one, we have here the phase shift between two sources. Okay. The ideal phase shift to parallel will be 0. Although, that is not usually practical. Okay. Typically, phase angle limits for paralleling two sources are positive, negative, 10 degrees or less. That's why here, we assign here the maximum synchronizing angle to be 10 degrees. We are using the maximum value, 10 degrees from here. Okay? So, two sources with different phase angle is that exchange of real power watts happens. If the phase shift between two sources is 0, no real power exchange takes place between two sources, which is what we want. We want power to flow to the load and not between the sources. Okay, so for the maximal angle difference, okay, to calculate for the maximum angle limit, we need to add the advanced angle plus the maximum synchronizing angle, which is 10 degrees. To get this advanced angle, here we are nominating the advanced time. This is usual industry practice to have 150 milliseconds. And the advanced angle, okay, we have here to calculate is 360 degrees over 15 seconds times the 150 milliseconds advance time. This 15 seconds, this is during the synchronizing, wherein one sleep cycle, it has to be one sleep cycle every 15 seconds. So we have here the phase angle limit to be, the result is 13, the total is 13.6 angle. To round off this one, okay, that's why we have 15 degrees for our maximum angle difference. And for our maximum frequency difference, okay, if one source has a slightly higher frequency than the source may come to perfect synchronization for brief time and then slip away into not being synchronized. Okay, if two sources with different frequencies are close, real power or watts flow between sources, which will vary depending on the relative phase angle difference between the waves, since the frequency of one source is slightly ahead. Phase angle keep changing throughout, and hence the real power also keep changing. Practical limits to frequency difference for paralleling the sources are generally 0.1 Hz or lower. That's why here we have assigned here for our maximum frequency difference, okay, to be 0.07 Hz, which is lower as required for which is the requirement for 0.1 Hz. Okay? Okay? This is in 1 second. Okay? This is for 1.19 second. Okay? let's come back for the maximum angle difference. This is 15 degrees here. According to Buff book ANSI IEEE 242, the closing angle to be at least 20 degrees. So we are okay here because our maximum angle difference here being calculated is 15 degrees only. Okay. Next, for we need also to calculate the values for the voltage when it is the bus is dead and when the bus is live. So for the setting for the setting for the dead buses, okay, both bus A and bus B has to be okay at 30%. Okay, so that's why here our setting to 30% or below. That's why we have here 0.3 per unit. Okay, so this is for the to determine the buses to be a dead bus. Okay, for a live bus, it requires to have at least the buses to be 80% and above. So that's why here we have here a 0.8 per unit for bus A and for bus B. Okay? This is our time current curves, okay? And this is the curve for our subject relay, okay? And this is also this is the relay for the secondary, and this is the relay for the primary side of the transformer, okay? And we have here the transformer thermal and mechanical damage curve, okay? So by looking these curves, we could conclude that our transformer thermal and mechanical damage curve are, or our transformer rather, is being connected by both primary and secondary protection relays. Okay, so and also here, this is the curve of our circuit breaker. Okay, so all of these three curves here is on the left side, meaning there is we have performed a proper coordination between our transformer and our protection relays. Okay, so here this relay, this is for the primary side, okay, of the transformer. It's not we did not tackle this one. Later on our next video, we will be discussing also a relay setting calculation for our upstream relay for the primary side of the transformer. Okay, thanks for watching.